if you look at our objectives for today, you'll see that you're going to be able, by the end of class, to write electron configurations, even if I only give you a period and a group number. And based on an electron configuration, you'll be able to tell me what something's period and group number are, even without the use of the periodic table. Okay? Now, it sounds a little far-fetched, but we're about to uncover some fundamental things about the structure of the periodic table that will help with that. We have already established that elements on the periodic table are organized into groups or columns with other elements that they share physical and chemical properties. Okay? In addition to this, now we're going to learn about how they are in rows or periods based on their electron configuration. Okay? Okay. There are a total of 7 periods on the periodic table. That's why it's in 7 rows. Okay? So a period is the same thing as talking about a row. The length of each period is determined by the number of electrons that can be held by the sublevels being filled in that period. Okay? Let me explain what that means. Okay, in period 1, this period right here that has hydrogen and helium in it, we are filling the 1s sublevel. So we're in the first energy level and we're filling the s orbital. How many electrons can the s orbital hold? 2. Which is why that period is only 2 elements long. Hydrogen and helium. That's it for that row, right? In the second row, we've moved up to the next energy level, and we're now filling the 2s and the 2p sublevels. So how many electrons can be held in the 2s sublevel? 2. And in the 2p? 6. So in total, 8, which is why there are 8 elements in that row. The same is true of period 3. And then when we move up to period 4, we are adding a d orbital, which means we're adding 10 additional electrons that can be held. So we're adding 10 additional elements to the row. The same pattern continues for 5. And then in period 6, we add an f orbital, which can hold 14. So we add 14 additional electrons, which means there can be 14 additional elements in that row. Now, that would make our table horrifically long, so we don't leave those 14 in the row. We drop them down into the lanthanide and actinide series instead. But they should be in that row, which would make that row an additional 14 elements long. And the same is true for period 7. These numbers look familiar? This pattern of 8, 8, 18, 18, and 32? Yeah, they should look familiar because that's what we said is the difference between the atomic numbers of these guys going down in their groups. And this is why. It has to do with their electron configuration. Okay. So, because of this, the periodic table can be broken into blocks. So you had questions on your pre-assessment about what does a block mean? What does it mean by what block is it in? Okay, it can either be in the S, P, D, or F block. And what that means is in that section of the periodic table, which orbital is currently being filled. If you're in the S block, then the s orbital is being filled. If you're in the p block, the p orbital is being filled. If you're in the d block, the d orbital is being filled. And if you're in the f block, then the f orbital is being filled. This is a map of what the blocks look like. Okay, so in blue, we have the s block, which is all together except for helium, and we'll talk about that. We'll talk about why that is later. Okay. Then in green, we have the P block, and in pink, we have the D block, and in yellow, we have the F block. Okay? So what that means is just that if you are in this block right here, currently the s orbital is being filled. Okay, so for hydrogen, it's the 1s orbital that's being filled, right? And for lithium and beryllium, it's the 2s orbital. And for sodium and magnesium, it's the 3s orbital, and so on and so forth. But it's always the s orbital that's being filled here, right? And the same thing is true if we come over here. What they're saying is if you're in this block, then your p orbital is being filled. Again, with the exception of helium, which we will discuss later. Okay? That's why these blocks are broken up the way that they are. And we can use that information as a helpful way to help us write electron configurations without even having to look at the periodic table. All right? So, an electron configuration can be used to determine the period of an element. Arsenic's electron configuration is AR, because we're doing noble gas notation here. So argon in parentheses, and then 3d10, 4s2, 4p3. What is the highest energy level being occupied by arsenic? 4, right? N equals 4. Oh, it just showed up on there. I didn't even need to draw it. I forgot I had written it. Okay, so the 4 out there in the 4s2, 4p3 indicates that the highest energy level for arsenic is 4. I drew this picture last period and it seemed to really help them, so I'm going to draw it again for you guys. Okay, so think of it like this. We have the n equals 1 energy level here, right? And it has the 1s orbital. It just has one of them. And that's the first energy level. In the second energy level, we have 2s and 2p. In the third energy level, we have 3s, 3p, and 3d. And then as we continue out, in the 4s energy level, we have 4s, 4p, 4d, and then eventually 4f. Okay, so when I ask you for the highest energy level, I'm not asking you for the orbital. Okay, I'm not asking for S or P. I'm asking for the number. Are we in the 1, 2, 3, or 4? And in this case, because it has 4s2, 4p3, there are electrons in that fourth energy level, so N equals 4. Even though it has the 3d there, there are electrons in that 3d orbital, but they are also in the fourth energy level. This would be the case even if it was 4s2, 3d5, because even though the 3d orbital isn't all the way full, there are still electrons in the 4s orbital, which means we are in the fourth energy level. Okay? All right. Whatever the highest energy level is the period that that atom is in. So if you have something that says, 3s2, 3p4, your highest energy level is the third one. You have not moved up into the fourth energy level yet, so you are just in the third energy level, which means you would be in the third period on the board. The reason why, and I'll pull back to the table for this one. The reason why this row of electrons is in the fourth period, even though it's the 3d orbital, is because you have to fill the 4s first, right? Because of that fill order that we talked about, the energy levels. 4s is slightly lower energy than 3d, so it fills first. And so that's why we put this block here, even though it's technically in the third energy level, it fills after the fourth. So we just put it down a row to help us remember that it fills after. All right. We're going to write simplified group notations for each group or each column on the periodic table. And when we write those, they will be for the outermost energy level, for the outermost shell of the electron, or of the atom, and they will be written where N equals the highest energy level of that atom. When we get to one, I'll explain it to you. Let's start with the S block. We're going to talk about group 1, which is the alkali metals, and right there in parentheses you can see their group notation. Okay, so the reason this is a group notation is because it's accurate for all of them. It's saying the outermost energy level for all of these is NS1. So for hydrogen, it would be 1S1. Because remember that the N equals the highest energy level occupied. For lithium, it would be 2S1. For sodium, it would be 3S1, and so on down the group. So they're saying these guys have one electron in their outermost shell, and it's in that S orbital. So it's always going to be, whatever the energy level is, S1. They have one electron in their outermost shell. They are silvery in appearance. They are metals, but they are soft enough to cut with a butter knife. So if you are thinking about a metal as something that is very hard, not the case here. They are incredibly reactive. So having that one electron in their outermost shell is what makes them reactive. They would rather have 8, and it's easier for them to lose one electron and go back down to a shell that's full than it is to gain 7 electrons, right, to try and fill it up. So because they only have one to lose, they're very willing to give that electron away, which means that they are willing to react with just about anything. And being so reactive means that you're not just going to go out into the ground and dig up pure sodium metal. Because if you put pure sodium metal into the ground, it's going to react with something that's in that ground. And it's going to be a compound. So you're much more likely to find sodium in a compound in nature. They also react vigorously with water, and when they do that, they release hydrogen gas. So they're just very reactive overall. The second group is the alkaline earth metals, and their group notation is NS2 because their s orbital is filled, right? If you look at beryllium and magnesium and calcium, they're all in the s block, but their s orbital is now full. 2 electrons in their outermost shell. They are harder, denser, and stronger than group 1, though that does not necessarily mean that they are super hard, super dense, or super strong, because the first group is not very hard or dense or strong, so being more than that doesn't say a lot. They have higher melting points than group 1, and they are also less reactive than group 1, but again, group 1 is incredibly reactive, so even though they are less reactive, they are still rarely found out in the world unreacted and not in a compound. Hydrogen and helium. Before we move on to discuss the other blocks, we need to talk about these two because they are exceptions to the rules. Hydrogen is part of group 1, but unlike the alkali metals, it is not highly reactive. And it doesn't share a lot of similarities with the other elements in that group. We put it there because it has one electron in its outer shell, and therefore it should go in that group. But it's really not similar to that group, and quite frankly, it's not similar to really any other group on the periodic table. Hydrogen's kind of an outlier. It's very unique, and it doesn't really fit into a group. So we elected to leave it in this column because it doesn't fit better with another group. So we decided we'll leave it where its electron configuration puts it, even though it doesn't fit with the other alkali metals, which is why you will notice it is a different color on my periodic table. It is not, though it is in group 1, it is not classified as an alkali metal. Helium has 2 electrons, and therefore it should be in group 2, right? However, here's the difference, okay? And we're going back to that funny picture that I drew, right? We have the 1s orbital here, right? 1s, and then we have 2s and 2p, okay? Helium, when it has 2s2, this orbital is full and complete, right? Okay, if we go on to the 2s orbital, okay, for beryllium, okay, if we fill up 1s and we fill up 2s, even though this has no electrons in it, it's still out there existing, which means that the outer shell for beryllium is not filled, which means it's not as stable as helium is. Helium, like the other noble gases, even though it doesn't have 8 electrons in its outer shell is still full because the first energy level only has the 1 orbital. So it's completely full, which makes it remarkably stable, just like the other noble gases. And therefore, because it fits with that group in terms of chemical properties, we moved it over to be on top of the noble gases. So it fits better, and it got moved over there. It's still part of the S block, but it's just in a different location because it doesn't fit with the alkali earth metals. It fits with the noble gases. The D block. If you look over here, group 3 starts off the D block for us, this section right here in the middle, okay? And if we wanted to write their group notation, we would have to write N-1 D1 NS2. So what that means is, let's take scandium, okay? It's in the 4th period, which means N equals 4, right? So 4 minus 1 equals 3. That makes sense because the 3D orbital is right here. So 3D1, 4s2. Because this s orbital is now full. So anything in this column, their s orbital is full and they're filling the first one of the d orbital. But the d orbital is always going to be of the previous shell, which is why we have the n-1, right? You fill 4s2, 3d, 5s2, 4d, right? It's always the previous one because it's just slightly less energy. Okay. Groups 4 through 11, we don't do a group notation like we just did for group 3, and that's because, if you remember, there's a lot of exceptions in how these d orbitals fill. So a group notation would be off and on correct, so we just don't do it for these groups. And then group 12's notation, we have that d orbital all the way full, so this time it's d10. And then the s orbital is still full, so it would still be, if we're looking at zinc, it would be 3d10, 4s2. These elements that are in the D block are called the transition elements, so groups 3 through 12, all of them are the transition elements. Okay? They are all metal, which means they're good conductors of electricity, okay? Have all the other properties that go along with metals, and they are typically less reactive than the elements of groups 1 and 2. In fact, some of them are so unreactive that you can actually find them in their pure state in nature, like gold. Gold doesn't react with a lot of things, which means it would be possible for you actually to go out and dig in the dirt and find pure gold, because it's not going to need to have reacted with something in order to be stable. Let's talk about the P block. Group 13 starts off the P block for us, and its notation is NS2, NP1. So whatever your N value is, which is also, as we discussed earlier, your period number, is going to be the N value in this equation. So for sodium, well, sodium's not in the P block. Let's do aluminum, okay? Aluminum's group notation would be 3s2, because the 3s is full, and then 3p1, because it's the first one filling an atom into the p orbital. Group 14's notation is ns2np2. Group 15's is ns2np3, and I'm sure you can see the pattern and fill in that it would be one more in the p orbital for each of them as we go across the period to the right, all the way up until we get to group 18, and theirs is going to be ns2np6, which means they have 8 in their outer shell and are therefore stable. For p-block elements, and this only works for p-block elements, you can take their group number minus the number 10 and find out how many electrons they have in their outer shell. Okay, so if you look at group 14, 14 minus 10 is 4. Those have 4 electrons in their outer shell. So let's look at this outer shell thing again, because I just want to help clarify a little bit, okay? I'm just going to draw here on a plain white background, okay? So the first group, we said group 1 had 1 electron in its outer shell. And then group 2 has 2 electrons in its outer shell. And then we jump over to 13 and say they have 3. So why do we just entirely skip the D block when we're talking about outer shell electrons? The reason is because the D block is filling in an orbital from a lower energy shell, so you are not changing the number of electrons in the outer shell. Here's what that looks like, okay? We have, like we said, the 1s in the center. That's n equals 1 energy level, just has the 1 orbital in it. Then in the second energy level, we have the 2s and the 2p. In the third energy level, we have the 3s, the 3p, and the 3d, okay? And in the fourth energy level, we have 4s, 4p, 4d, and eventually 4f. Okay? So as we fill in, we fill 1s, 2s, 2p, 3s, 3p, and then we skip up to 4s, right? We skip over 3d, correct? Because 3d is slightly higher in energy than 4s. So the Aufbau principle says we're going to fill 4s first. So now this has 2 electrons in it, but the next electrons don't go into the 4p, do they? We go back and fill in 3d. So we can add, 1, 2, 3, 4, however many we want to add here for the D block. Are we changing how many are in the outer shell? No, the outer shell is staying the same, untouched. We're filling an inner shell orbital. And then when we get to gallium, and we've totally filled in the 3D orbital, then we jump back out to 4p and add 1. Now we've changed the number of electrons in the outer shell, which is why we go from calcium that has 2 in its outer shell all the way to gallium before we change to having 3 in the outer shell. Does that make sense? Okay, just wanted to make sure we were clear on that. Okay. The P block has main group elements in it, okay? Not all of the main group elements are in the P block, but some of them are, because the main group elements are groups 1 and 2, and then groups 13 through 18. So we have main group and transition elements. Transition elements are the D block, main group elements are 1 and 2, and then 13 through 18. The P block has a weird variety of elements in it, okay? It contains all the nonmetals except hydrogen and helium. It contains all 6 of the metalloids, and it contains a bunch of P-block metals. So we're kind of running the spectrum. When we talked about the S block and the D blocks, they were all pretty similar to each other. The same is not true of the P block. They are kind of all over the place. It also contains one other group that's not the main group elements. It contains the halogens. The halogens are in group 17, which, if you're doing the math, means they have 7 outer shell electrons. And if you remember, the magic number that we're trying to get to is 8, which means, because these guys only have 1 to gain, they are also incredibly reactive. These are some of the most reactive nonmetals on the periodic table. They want to react with everything in order to get those 8 outer shell electrons and become stable. The last block we need to talk about is our lovely friend, the F block. Okay? This is wedged down there between groups 3 and 4 in periods 6 and 7, more commonly known as the lanthanides and actinides. On our modern periodic table, it's dropped down below the table so that the table isn't unwieldy and wide, but the elements really do belong there in groups 3 and in periods 6 and 7 between groups 3 and 4. Okay? Like the D block, these orbitals fill in a weird order, meaning their outer shells are not consistently the same, so we don't have a group notation for them. And also, as you fill them, you're not going to affect your outer shell electrons, just like with the d orbital. The lanthanides, which are in period 6, are shiny metals, and they are very similar in reactivity to group 2. In fact, when the periodic table was originally being developed, there was a lot of disagreement about where to put these guys because a lot of people thought they belonged in group 2 with those alkali earth metals. And then the actinides are in period 7, and they are all radioactive. Every single one of them is radioactive and will decay over time. Also, on top of that, only 4 of them have been found naturally on Earth, the first 4 in that group. The rest of them have only ever been synthesized and measured in a laboratory. Is it possible that they exist out in the world without our knowledge? Yes. Is it likely? No. They have very short half-lives. They are going to decay into other elements very quickly, and so they have only ever been measured in a laboratory. All right, before I send you off on your own to try your homework, I want to do an example problem on the board for you, okay? So we're going to go back to a nice blank whiteboard here, okay? If I were to tell you that a element was in period 4 and group 5, okay, you should be able now, with a little practice, obviously, to tell me the electron configuration for this atom without having to look at your periodic table. Here's how we would do it, okay? It's in period 4. What does that tell me about its energy level, of the outermost energy level? 4. It's 4, right? So we know N equals 4. Okay? I meant group 15, not 5. That's just a mental error on my behalf. Okay, being in group 15 tells us that it is in the P block. Okay? And you can refer back to your notes to remember which groups are in which blocks. I'm more than okay with that. I just don't want you to look at the periodic table proper, okay? So, knowing that it's in the P block means that we can take 15 minus 10 to find out how many outer shell electrons it has, which is 5 electrons in the N4 energy level. Okay, so what that tells me is that it has to have 4s2, 4p3, right? If it's going to have 5 electrons in its outermost energy level. And then I know, just because of essentially the Aufbau principle, that we're not filling higher energy levels until the ones lower than this are full, right? So everything under this is also full. which means I can write the full electron configuration. I can say 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, 3d10, 4p3. And there's its full electron configuration. I didn't have to look at the periodic table even once. Okay, you're gonna have to take some time to remember which blocks are where and which groups are in which blocks, but eventually you'll be able to do the same thing, I promise. We can also reverse engineer this, right? If I want to know what energy level, what group this is in, right? I can look at this electron configuration notation and say, okay, well, the outermost energy level, I see a 4, so it has to be in the 4th period, so I know it's in the 4th row, and then I see that it's got 3 electrons in the p block, which means it's going to be in the 3rd column of the p block, so that should be group 15. Okay? It will take practice, and that's okay. All right, go ahead and reopen that pre-post quiz and try your hardest on it, okay? If you get stuck, I'm more than willing to help you. Refer back to your notes to find out what blocks are what, but just don't be staring at the periodic table while you're trying this, okay?